Mass wasting has to be the unsung hero of all geological processes. I say unsung because unless it was for the occasional landslide, most people would even know these things are going on. So mass wasting, a very, very important process, as we'll find out. And to start our discussion, let's go back to those products of weathering, the solid products of weathering. We're talking about that mixture of rock fragments, largely clay minerals now. Remember, that was the big batch of the solid particles. Quartz, and a little bit of iron oxide for color. Now, all that stuff mixed together as it accumulates above bedrock, which is the unweathered rock below, we call that regolith. Now, the interesting thing is, once this regolith forms, there's a series of processes that are set into play, the purpose of which is to pick that stuff up, haul it away, and dump it in the ocean. Now, what happens to it out in the ocean? Well, we've already talked about that. Products of weathering are converted into sedimentary rocks. That's where most of your sedimentary rocks form, from the stuff dumped out into the ocean. Well, the bottom line is the process that gets that whole process started is mass wasting. Now, with one notable exception, and there always seems to be one notable exception, the thing that characterizes all of these processes of mass wasting is that the distance traveled is relatively short. For example, all the processes except for one, the material is only moved, for the most part, from hilltop to valley floor, and once it gets the stuff to the valley floor, the job of mass wasting is over. Why? Because once it gets to the valley floor, now we have processes of erosion that are ready to take over. For example, the absolute number one agent of erosion, we'll talk about this in another lecture, are streams. Streams are the most... Wherever water can exist, that's the rule. Wherever water can exist, it's going to be the number one agent of erosion. Well, you think about it, every valley has a stream in it. Now, there might not be water in it all the time, but every valley has a stream because you're going to find out that that's where the valley came from. It was carved by the stream. Well, anyway, once mass wasting gets this regolith down to the edge of the stream, dumps it in the stream, then the stream hauls it off, and eventually where? To the ocean. Because the fact of the matter is, with the exception of the few or whatever short streams and deserts which head up in some highland area and just come to an end within a basin, don't really go anywhere, all the streams in the world eventually end up getting to the ocean. So there's your little, the job has been completed now. The other thing that could be in the valley are glaciers. Now, we're going to talk about glaciers too. Glaciers are really good at picking stuff up and carrying them away. They really are, but obviously, glaciers can only exist in certain places where it's cold enough to have them, but when they are there, they are really good agents of erosion. Now, there are some glaciers that do indeed carry the material to the ocean. For example, the glaciers coming off Antarctica. They go right to the edge of the continent, they calve, they dump their stuff right directly into the ocean. There are other glaciers, for example, that flow into fjords. For example, in Scandinavia and Alaska. You don't have to go to Scandinavia to see fjords. But the fjord is part of the ocean, so that glacier, again, provides the stuff directly to the ocean. Most glaciers, or at least a lot of them, don't make it to the ocean. A lot of glaciers get to a certain point where they melt because of the change in climate and weather. But the thing is, once they melt, now we're generating water that creates streams that pick up the stuff that they dumped and eventually make it to the ocean. So between those two guys together, this stuff is hauled off to the ocean. Now, here's the important thing about mass wasting. The driving force in mass wasting is gravity. And I think that's what really separates mass wasting from erosion. Students often ask me, well, why isn't mass wasting just another form of erosion? Well, some people do have it that. Some people consider mass wasting as one of the kinds of erosion. But in my mind, I like to separate them out because the difference being that although gravity obviously is involved in streams, they're flowing downhill, and it obviously is involved in glaciers, as we'll find out. They're either flowing downhill or they're being forced across the surface by heading to the ocean, which is always downhill. The thing that does the work in the case of streams is the water. I mean, gravity's involved, but the water does the work. In the case of glaciers, gravity may be involved, but it's the ice that does the work. But you see, in the case of mass wasting, it's gravity that does the work. So in my way of thinking, I always sort of like to set it offside as a different kind of a process now. So if you want to consider it an agent of erosion, that's okay with me. Okay, well, anyway, gravity. And although I think everybody knows what gravity is, this mysterious force that keeps us from flying off into space and brings things down that you throw up in the air like baseballs and footballs and airplanes, I think we want to talk about gravity a little bit just to sort of put it in context of this discussion. Gravity was the brainchild of Isaac Newton. Now, a lot of people think that Isaac Newton was probably the most intelligent person who has ever lived. And from what I've read about him, I think he may have been. He's a little strange at times, but I think he was still pretty sharp cookie. Now, the story goes that Isaac Newton was living in London, and this was at the time the bubonic plague was sweeping through Europe, and fearful that it was going to get to London, he took off to the countryside. Now, while he was out there, he was only out there for a couple of years, and he was only 21 years old. 21 years old when he did all this stuff. Out there in the country, I guess he had a lot of time to think. And what he did, he came up with things like, well, we're going to talk about the theory of universal gravitation. He came up with that. He came up with all the rules that govern motion of anything, whether it's your car or a space vehicle or a planet. He came up with all of those out there. And the other thing he did, and this just really boggles my mind, apparently when he was trying to work up all these intricate processes, the mathematics of the day weren't strong enough, powerful enough to let him to do it. So what he did, he invented calculus. Now, I can't hardly even imagine that. It was tough enough getting through it, let alone inventing it. So anyway, he invented calculus. Well, one of the things he did, he came up with this idea of gravity. And basically, here's all he said. He said that every body in the universe attracts every other body in the universe with this force called gravity. And he said the force was very simple. He said the force was proportional to the product of the masses of the two bodies, how much stuff each body contains, and it was inversely proportional to the distance squared between their centers of gravity. Now, just centers of gravity for a moment, that's simply a point within the body around which the mass is sort of uniformly distributed. Now, obviously, in a sphere, it would be dead center in the sphere. If it's an odd-shaped body like yours and mine, then it's somewhere probably within our guts, not in your hand or your head, you see. So in other words, that's the center of gravity is. Now, the squaring of that distance value, the big thing about the squaring, that simply makes the force of gravity change really fast. For example, if the bodies are moving away from each other, the force drops off very fast. If they're approaching each other, it increases very fast. So that's what the square does. So basically, that's all he said. But here's the important part. He said every body with every other body. Well, we normally think of things like the gravitational attraction between Earth and the Moon, or maybe Earth and the Sun, and that's okay. But it's also, note, Earth and Alpha Centauri, which is the next star, which is, 4 light years away. But it's also Earth and a star in the next galaxy, which is 2.5 million light years away. But note, it's also the force between Earth and you and me, keeping us on Earth. It's also the force between you and me and Alpha Centauri. It's also the force between you and me and a star in the next galaxy. See, he said everybody with every other body. There's no limitation on that. So that's sort of an interesting thing. But anyway, we're not really interested in the gravitational attraction between Earth and some distant body. We're really interested in this discussion between the force between Earth and some object sitting on its surface. Well, let's think about that. Some object sitting on its surface. That means that the force of gravity then, according to Newton, would be proportional to the mass of Earth times the mass of whatever this object is, maybe it's a big rock or whatever, your car, divided by the distance between their relative centers of gravity. So that's basically what he said. But let's talk about this object on the surface of the Earth. Question, what do you think would be the biggest object you can possibly imagine sitting on Earth's surface? Well, I think if you think about that, it probably would be some kind of a mountain peak, not a mountain range now, just a single peak. Well, I think, interesting enough, if you ask the average person, what do you think that peak would be? I think the average person probably instantly would probably choose Mount Everest, because over there in the Himalaya, you have Mount Everest rising to 29,600 and some feet above sea level. Well, that's pretty good, but if you look at where it rises from, the base of Mount Everest is probably, as I remember the topography, already about maybe 10,000 feet above sea level. So the mountain itself, let's say, is only 19 or 20,000 feet high, which is pretty good, but that's not the largest single mountain mass on Earth. And if you think about that, we've already talked about the largest single mountain mass on Earth, which is the Big Island of Hawaii. The Big Island of Hawaii is this shield volcano that builds from the ocean floor at a depth of about 15,000 feet below sea level. It rises, in the case of Mauna Kea and Mauna Loa, the highest peaks. They're almost exactly the same elevation at the summit, 13,000, I think it's 740 feet. So note, the Big Island of Hawaii is 29,000 feet by itself. That would be the largest single mass on Earth, the biggest thing you can imagine sitting on Earth's surface. Then, okay, let's apply his law again. It says that the force of gravity acting on the Big Island of Hawaii would be proportional to the mass of Earth times the mass of the Big Island of Hawaii divided by the distance between the center of the Earth, center of gravity, and the center of gravity of the Big Island of Hawaii. Now, if you think about a cone, where would be the center of gravity? It certainly wouldn't be at the apex, and it certainly wouldn't be at the bottom. It would be somewhere in between. So let's just guess and say maybe a third of the way up, which would be what? Maybe 2 miles. So if we wanted to put a number in there for that D, what it would be, well, it would be the 4,000-mile radius of Earth and 2 more miles. So it would be, let's say, 4,002 miles. But then I would ask you a question. Do you think that 4,002 miles, which is the actual distance between the centers of gravity, do you think that's statistically different from the radius of Earth, which is 4,000? Now, I guess we could argue that point, all right, but in my way of thinking, it really isn't. 2 parts out of 4,000? So I would say, no, they're not significantly different. So what I'm going to do, I'm just going to worry about that 4,002. I'm simply going to use the radius of Earth now as the distance between their 2 centers. So now note, we can rewrite his little formula and say, the force of gravity on the Big Island of Hawaii is proportional to the mass of Earth times the mass of that object, the Big Island, divided by the radius of Earth squared. Well, now note, if you look at all those little things, the force of the proportionality constant, of course, that's the universal proportionality constant, that is a constant. It's a number. You can look it up. The mass of Earth is a constant. I mean, Earth isn't getting any more mass. It isn't adding anything. Well, I know there's a meteorite impacts once in a while here and there, but the amount of mass contributed to Earth with all those meteorite impacts since it was beginning probably really doesn't amount them very much. In other words, the mass of the Earth was really fixed way back when we made that transition probably from the protoplanet stage. So the mass of Earth isn't getting any bigger. How about the radius of Earth? Well, it's not expanding at all. I mean, we understand now that you're creating oceans, but remember, you're also consuming ocean, so the radius of Earth isn't getting any bigger or smaller. So note, if you look at that formula, you've got 3 constants. You got the constant, which is the universal gravitational constant. You got the mass of the Earth, and you got the radius of the Earth. A constant times a constant times divided by a constant. If you take a number times a number and divide it by a number, what do you get? You just get another number, you see? So now what we can do, we can take those 3 numbers and make another constant. And we'll call this constant now Earth's gravitational constant. And so now we can rewrite that formula and say the force of gravity for any object on Earth's surface is proportional to its mass. Now that's really pretty simple. Now the proportionality constant now is Earth's gravitational constant because the 3 things we took out, well, one was the universal, but the other 2 were basically related to Earth. So here's what it says. The force of gravity that acts on any body sitting on Earth's surface is just proportional to its mass. And that makes a lot of sense. The more mass it has, the greater the force of gravity. Okay? Now here's a question for you. Can this force of gravity be measured? Well, yeah, sometimes it can be measured. It sometimes be a little difficult, perhaps, but let me give you an example of a measurement of the force of gravity. If you have a scale in your bathroom, maybe you did this morning, you stand on this scale, you put your mass, you see, on the scale. Inside the scale, there's some kind of a device, probably electronic nowadays, that takes into account that gravitational constant of Earth. And it reads out what? It reads out your weight. You see, that's what your weight is. Your weight is the force of gravity. So know what we're saying here. Weight is proportional to mass. Well, that makes a lot of sense too. As the mass goes up, the weight of the object goes up. The mass goes down, the weight of the object goes down. But that's not the important thing. Note, mass and weight are not the same. Weight is mass times the gravitational constant, so they are not really the same. Now, your mass, for example, is the same no matter where you would go in the universe, your mass would be the same. Take, for example, when the astronauts went to the moon, the Apollo project. When those guys got up to the moon, they had the same mass at the moon that they had down here. Your mass doesn't change. How about their weight? Did they weigh the same on the moon that they did down here? No, they didn't weigh the same. Why? Well, you're now dealing with moon's gravitational constant. Now, the moon's gravitational constant has to be smaller than Earth's because, for one thing, the moon is smaller, see? So it has to be smaller than Earth's, and it is. It's about a sixth. So let's say, to make my mathematics easy here, let's say one of the astronauts weighed 180 pounds down here on Earth. That was his weight. He went to the moon, same mass now. What would he weigh? Well, a sixth of that. So he would actually weigh in pounds 30 pounds. Remember all those big leaps those guys were making up at boing like that? The reason why they could do that, here they had muscles in their legs that were strong enough to throw a 180-pound body up in the air to get over a high jump, let's say. Well, now they only weigh 30 pounds. Of course, I know with all that stuff on their back sort of adds a little bit to it. But that's the reason why they were able to do that, is because their weight was so small. Now, here's another one. I just have to, this trivia stuff, but I love trivia. We have a space station out there, and we have astronauts out in the space station. They always show them out there floating around in the chambers and all. And they always say our astronauts are weightless in space. Question, are they weightless? Well, I don't know. Weightless to me means there is no weight. The weight is equal to zero. In other words, the force of gravity is equal to zero. Now remember your basic mathematics. The only way you can get a zero is to multiply a zero times a zero, or multiply zero times a number. Then you get a zero. So if they are truly weightless, then either the force, that gravitational constant has to be zero, or their mass has to be zero, or both. Well, their mass can't be zero. It isn't. They have the same mass up there that they had down here on Earth. So the mass is not zero. Now, could the gravitational constant be zero? Well, no, it can't. Because Isaac Newton said everybody in the universe is attracted to somebody. Which means there is a gravitational force involved here. Which means there is a gravitational constant. Now, it might be very, very, very small. So their actual weight would be very, very, very small. But they cannot be weightless. There's no such thing as weightlessness in space. I don't care where you go, you're always going to weigh something. Why? You have a mass, and you're always going to be attracted to somebody. Okay, enough for that now. Now, let's go back to a picture. We want to talk now about mass wasting finally and moving things on slopes. So let's start off. Let's say we have a horizontal surface, which we have here. Now, you put an object on a horizontal surface, coffee cup. Question, will that cup move? Well, no, it's not moving. Why not? Well, the actual reason why the coffee cup isn't moving, because in physics you'll learn that in order for any object to move on a surface of any kind, there has to be a force directed parallel to the surface. Well, note there is no force directed parallel to the surface. The only force we're dealing with is the force of gravity, and is perpendicular to the surface. So that's the reason why that coffee cup doesn't move. But note, if I were to bring a force in parallel to the surface, it would move. But as long as it's pushing, it'll move. But as soon as I take my finger away, it stops again, because there is no force parallel to the surface. So it sounds pretty simplistic, but this is important for our discussions. Any object sitting on a horizontal surface, I don't care what it is, I don't care the size, I don't care about the shape, it could be a perfect sphere, it could be a drop of water, I don't care what it is. No object sitting on a horizontal surface will move of its own accord, because there is no force directed parallel to the surface. The force is perpendicular. Now, here's what we're going to do. There's a series of drawings that shows this very nicely, I think. If we start to tilt the surface now we got a totally different picture. Once you tilt that surface, there are two new forces that are generated from the force of gravity. Remember, the force of gravity is always straight to the center of the Earth. Two new forces. One force is directed parallel to the surface, downslope. We call that the downslope component of gravity. The other force, I understand, is directed upslope, but I find it's easier for students to sort of comprehend all what I'm going to talk about if you visualize it as being perpendicular to the surface. Now, that force is the force of cohesion and friction. Cohesion means you stick together. Friction, by definition, is the resistance to motion. So here's a force that is cohesive, resistance to motion. So in other words, here you have two new forces. Question: what are the magnitudes of those two forces? How can we determine the relative magnitudes? Well, here's all you have to do to determine the relative magnitudes of those two forces, the downslope component of gravity and the force of cohesion and friction on any slope. All you have to do is to construct a box around that down to the force of gravity, using it as the diagonal, with one side, pair of sides, parallel to the slope and the other perpendicular. And if you do that, then you see your downslope component and the force of gravity, force of cohesion and friction, are limited by the sides of the box. Now, I get awfully tired of saying the downslope component of gravity, so I simply call that the go force, because that's what it is. It says to whatever's sitting on the surface, go. I get awfully tired of saying the force of cohesion and friction, so I call that the stay force, because both of those guys would say, no, don't go, you stay where you are. So we have a go force and a stay force. But note, if your angle of slope is, let's say, fairly shallow, the go force is smaller than the stay force. So my question to you would be, would an object sitting on a slope, let's say that's steep, maybe 20 degrees or so, would it move down slope? Well, I don't think so. Why not? The stay force is too big. It's bigger than the go force, so I don't think it would go. But note, if you just took this little sloping surface and picture it in mind now, it's just getting steeper and steeper and steeper and steeper. And watch the shape of that box. Once it gets, in our little discussion here, once it gets to 45 degrees, our box now is a square. In other words, the sides are of equal length, which means now we have a critical balance now between the go force and the stay force. If you were to increase the slope just a little bit more, then the go force now is greater than the stay force. Question: would the object move down slope? Well, sure it would. Why? The go force is bigger than the stay force, and that's the way it works. Now, here's the interesting point. This balance we talked about at 45 degrees, according to the way we've drawn these drawings in our minds here, it would be where the balance is reached. But experiments have shown that if you take now, this is important, solid particles of odd shape, not spheres, odd shape of any size at all, I don't care what the size is, and you pile them up like that, this angle where the balance is achieved isn't 45. I know it varies a little bit, but it's usually about 40. We call that the angle of repose. The angle of repose is defined as the angle beyond which materials will start to move down slope. So there's where your balance is reached, about 40. And you've seen it a lot. For example, in our discussions, we talked about cinder cones. You pile up cinders around a vent, 40-degree angle. That's your angle. We talked about stratovolcanoes. You build up that pyroclastic stuff and seal it off with lava. It's about 40 degrees. You take a canister of salt and pour it out on the table. The cone is about 40 degrees. A dump truck dumps anything. As long as it's solid and odd-shaped, it's going to have that angle of 40 degrees. So there's the secret angle now. The angle which the balance is reached is going to be 40 degrees. So what does it really mean? What it really means is that if the angle of slope is less than 40 degrees, then all of that regolith, that mixture of all the products of weathering, are just going to sit up there on that hillside. Why? Because the stay force is greater than the go force. But if the angle exceeds the angle of repose, or exceeds 40 degrees, then the go force becomes greater than the stay force, then all that stuff will start moving down slope. So the point is, in all these processes of mass wasting, which we'll talk about individual kinds of before we're done, whether they move or not is simply a function of the relative magnitudes of the go forces and the stay forces, and that's what determined by the angle of the slope. Now, before we go on any further, I want to say a few words about the effect of shape now, because that's a very critical point. I said this 40 degrees is sort of an average kind of thing. Well, the reason why it's an average is because if you can think about the particle sizes changing shape from something that's really irregular, let's say the most irregular thing, of course, would be a sphere, that number really is going to change. Let me give you a really, really good example, or what I think is a good example. A couple of years ago, I was on a field trip up into upstate Minnesota, and that's where a lot of our iron ore comes from up there. And they mine this stuff, and when they bring it into the plant to process it, it very definitely is odd-shaped particles. They've just scooped it up after they blasted it out of the open pit up there. And so I was looking around, and here were these stacks of the ore as it was being delivered to the plant. And you could just see, I just sat there and looked, but there's your 40-degree angle, because this stuff is fairly large chunks now, but they're still odd shape. Remember, size doesn't make any difference. It's the shape that does. So here were these odd shaped chunks, and there was that 40-degree angle. And we had students with us, and I made a great point to point that out to them, because they really don't believe me sometimes when I tell them this stuff. But anyway, what they do with it up there, they process it, and then they process it into spheres, these little taconite pellets. They're maybe about a ½ inch in diameter, and apparently the reason why they do that is because it's easier to ship and to unload and things like that. So once they made these things into these little spheres, and they're almost perfect spheres, about a ½ inch in diameter, then they bring them out and they pile those up until they're then sent off wherever they're going to go. And you look at that pile, and here's that pile. The angle of repose was far less than 40 degrees. Why? It's the shape that made a difference. So if you drive around the world and you go to places like that, look at those pile surfaces. If you see one where you're talking about 40 degrees, or it looks like it's about 40 degrees, then you don't even have to go over there. You can just assume that if I went over there, what I would see would be odd-shaped particles like that. But if you see a pile of stuff someplace and the angle is less than 40 degrees, right off the bat, what that tells you is if I went over there, what I would see would be particles that were not anywhere near odd shape, probably approaching these little spherical shapes. So anyway, that's a big thing in terms of mass wasting and the movement of materials. Now, what I want you to do, and what I'm going to do next, is to sort of set the scene for our next discussion. What I want you to do is to just imagine driving out in the country. And I hope you do this anyway, because this is the reason why you take courses like this. You want to use what you learn to look at what you see as you're driving to work or wherever you're driving to, and look at what is around you and see if you can understand why it's the way it is. So what I want you to do is think about driving around and looking at hillsides, and looking at hillsides perhaps that are obviously less than 40 degrees. And if you look at that hillside at less than 40 degrees, what does it look like? What would you expect it to look like? On the other hand, picture driving around and looking at a slope that's greater than 40 degrees. What would you expect it to look like? Would it be different? Would it be the same? If it's different, why? See, that's, I think, the whole beauty of a course like this. This is the beauty of geology in general, learning about the Earth. It allows you to understand what you see out there. And that's the whole purpose that I'm here talking to you. Well, anyway, we'll pick it up there, and I want to show you basically the things to look for and things that you've already seen, but hopefully now for the first time, maybe first time, you'll understand it. So we'll see you on the next talk.